long anticipated review for the physics test number 3. So we're going to start off with inductance. So remember, inductance, well, actually, impedance is the right word. Sorry about that. Impedance is something we use for AC circuits to analyze the interaction between resistors, capacitors, and inductors. So the problem is going to be something like this, just like we had in the example. So if you feel comfortable with the stuff we've already done, you can skip this. But so you have a voltage source that's going to have a sinusoidal. It's going to be sinusoidal. And let's say we have a 500 ohm resistor and okay, so we got a capacitor here which is going to be 0.21 microcoulombs and we have an inductor which is 46 millihenries. And the voltage input is going to be a maximum of let's say 2.1 volts. So what we want to find out is what is the maximum current, what is the RMS voltage, and what is the IMS, the RMS current, the impedance, the phase angle, and I think that's it. So this is the procedure you follow. So you have three different kinds of what we call reactances. We have the resistive reactance, which is just the resistance. We have the capacitive reactance, which is 1 over 2 pi f times c. So I need to give you the frequency here. So the frequency of the signal is 1200 hertz. So let's go ahead and calculate it. 1 over 2 pi times 1200 times 0.21 microfarads. So you got to remember to put the 10 to the minus 6 there. So 1 divided by 2 divided by pi divided by 1200 divided by 0.21 e to the minus 6th is 631 ohms. So all of these have 632 ohms. These all have units of ohms. The inductive reactance is 2 pi f times L, where L is the inductance. So we get 2 pi times 1200 times L, which is 46 times 10 to the minus 3rd henries, millihenries. 2 times pi times 1200 times 46 e to the minus 3 power, and I get it equal to 347 ohms. Okay, they're all ohms. Now you don't just add them all together. You've got this geometric relationship. So it says that the impedance, the total resistance to flow for this AC circuit, is x sub r squared plus x sub L minus x sub C squared. So you just take the three numbers you've gotten here, 500 ohms squared plus X sub L, which is 347 minus 632 quantity squared. So we get 500 squared plus the difference, 347 minus 632 quantity squared, and then take the square root of the whole thing. So we get the impedance is 576 ohms. And so for AC circuits, instead of using Ohm's law with resistance, you use Ohm's law with impedance. So instead of V is equal to I times R, it's V is equal to I times Z. So if we solve with the current, we'll get it's the voltage divided by the impedance. In this case, our maximum voltage is 2.1 volts, and we divide by 576 ohms. So that is 0.0036 amps. We'll rewrite that as milliamps. So it's, you multiply by 1,000, and this is the maximum. So if you use the maximum value. Okay, so the maximum voltage is going to be 3.6 milliamps. So divide or multiply 0.0036 by 1,000 millis per normal unit. And then you can we can calculate the phase angle. It's the inverse tangent, and there's no absolute value here, but it's going to be 347 minus 632 divided by 500. So it's the difference in the reactance of the capacitor and the inductor. So this can either be plus or minus because the tangent, the inverse tangent function goes from negative 90 degrees to positive 90 degrees. And you got to make sure your calculator is in degrees. And apparently I did something wrong there. Let's try it again. Negative 30 degrees. So that's the phase angle. And the phase angle is the difference in time between where you have a maximum in voltage and a maximum in current. They don't line up exactly. As far as the RMS current, you just take the maximum current and you divide by the square root of 2. So 3.6 divided by the square root of 2 is 2.5 milliamps. And you can do the same thing with the voltage. The RMS voltage is the maximum voltage divided by the square root of 2. So that's what was the voltage? 2.1 volts divided by the square root of 2. So that's 1.5 volts. And the last thing is, if you want to know how much power is dissipated in the circuit, what you can do is you can take the RMS voltage times the RMS current times the cosine of the phase angle. So if the phase angle is 0, you get 1, and it's just the RMS current times the RMS voltage, because the voltage and the current are in phase. But if they're out of phase, then you have to take that into account. So we're going to have 2.5 milliamps, so we've got to convert that back to amps. Voltage is fine, 1.5 volts, times the cosine of negative 30 degrees. And remember, the cosine goes between negative 90 or 0 and 100, but it still works out right here with the negative sign, even if you have a negative phase angle. 2.5 e to the minus 3 times 1.5 times the cosine times the cosine of negative 30. And so we end up with 0.0032 watts, or 3.2 milliwatts. Okay, so that's impedance. The second problem thing out of that chapter is a transformer. So a transformer consists of a primary side, which we'll call 1, and a secondary side, which we'll call 2, and they usually have different number of loops in the coil. So you have an N1, you have an N2. This is, there's some load on this thing, like your computer. So what happens is you've got current flowing through here, you've got I2, you've got across the secondary side, you've got delta V2. I'm going to use delta here. So it's a change in voltage. That change in voltage is going to drive the current in the second loop. So this is my secondary side. And over here you've got some source. So this is primary side. So this would be like your wall outlet. So there's a voltage. If you measure the voltage across this loop, it'll be delta V1. Now it turns out that the important number here is the RMS voltage, because for a transformer to work, you have to have a AC signal. And so for an AC signal, you could use the max or you could use the RMS. We want to use the RMS voltage drop across each one of these. And then there's going to be some current that's flowing through here. So you have current flowing through the primary side. It induces the time-varying current, creates a time-varying magnetic field, which then induces a voltage and hence current in the secondary loop. And so the relationships are such. So V2 over V1 is equal to N2 over N1. So if N2, if you have more loops on the secondary side than the primary side, then you have a voltage increase. If it's the other way around, then you have a voltage decrease. If you have an increase, it's called a step-up transformer. If a decrease in voltage, it's a step-down transformer. The ones that we use on the walls for charging our computers are step-down. They're going from 120 volts down to about 20 volts. So that's the relationship between voltage and number of loops. Now, as far as the current, what we assume is that the power is conserved. And again, we'd use the RMS values here. If I don't say it's RMS, you assume it's RMS. Okay. And the same thing's true for the current here. They're the root mean square values. So current times voltage is power. So we're conserving energy or power across these transformers. So typically you're given 3 out of 4 things in both of these. You might be given the voltage 1 and the number of turns. You can calculate voltage 2. Then you could use voltage 2, current 1, voltage 1 to calculate current 2. And because of this this relationship here, you can also relate the current to the number of turns, and it's the opposite of what it is here. So if you have more turns, you're going to lower the voltage, but you'll decrease the current. So these two things have got to switch. And you kind of see if I took the middle out here and I just cross multiplied, I'd end up with the second equation. Okay, so that's transformers. It involves alternating current. And these relationships come from the fact that the magnetic field created by the primary loop induces a changing magnetic field in the secondary loop, which then induces a voltage. Okay, so those are the two topics from chapter 21. 22, the main thing there, there's the two main things, the three main things. This is to do with reflection and refraction. So you can have reflection from surface, and you have an angle of incidence, and you have an angle of reflection. So this is reflection, and if you draw normal to the surface, no matter even if the surface is curved, you draw normal to the surface, it just says that the angle of incidence equals the angle of reflection. The second situation here is the refraction. And it depends whether you're going from a higher or a low index of refraction to a higher index of refraction, or you're going the other way. So if you have this scenario and you draw normal to the surface, now it's not going to reflect, but it's going to refract. And what will happen here is you have your angle of incidence and your angle of reflection. Here R stands for reflection. And there's two index of refraction. So in this scenario, when you go from lower to higher index of refraction, the ray of light bends towards the normal. So that means that the angle of refraction is less than the angle of incidence. And the specific relationship is called Snell's law. So it says N1 times the sine of theta 1 equals N2 sine of theta 2. Now, in this case, theta 1 is the angle of incidence, and theta 2 is the angle of refraction. Now, the other scenario is if you go from a higher index of refraction to a lower index of refraction. So the light's going this way, still going this way, but now the interface is different. What happens is that, let's call this theta 1 this time. I'll call this theta 2. So it bends away from the normal, but Snell's law still applies. N1 sine theta 1 equals N2 sine theta 2. Now there is some critical number, theta 1, when it gets large enough that it will actually bend. So here, let's see, we've increased this angle. What will happen is it'll bend away from the normal. It'll actually do this. So theta 1 is some value, and theta 2 is equal to 90 degrees. It's this angle here. So that's called a critical angle. And if this angle theta 1 is greater than this critical angle, then you're going to get total internal reflection. So the way you solve that problem, let's say N1 here is 1.7 and N2 is 1. So we're going from some glass into the air. That's why it's bending that way. You'd have 1.7 times the sine of theta 1 is equal to 1.0 times the sine of 90 degrees. Well, the sine of 90 degrees is 1. So you get sine of theta 1 is 1 over 1.7. Or theta is equal to the inverse sine of 1 over 1.7. And I've still got my calculator in degrees. So I come up with theta 1 equals 36 degrees. So what we can say, so if theta 1 is greater than or equal to 36 degrees, we have total internal reflection. Okay, well, I wanted to work a problem that I'm going to put on the test, and I'm going to show you how to work it. It won't be the exact numbers, but I wanted to do a problem which was a little bit harder than what we've done, more so because people who just copy equations down and they don't watch the review, they're hurting themselves. So I wanted to work one here where you get some credit for paying attention to what I'm doing here, taking good notes. So what I have is I have a light ray that's coming in to a flat surface. So here's the surface. And because this is an index of refraction of 1 and this is an index of refraction of 2, the light ray bends towards the normal. So theta 2 is going to be less than theta 1. Then it goes through this transparent material till it reaches the interface, which would go back out to air. And what I want to know is what theta 1 has to be so that you get that total internal reflection. So we kind of have to work our way back from here, that this is 90 degrees, this angle between the normal is 90 degrees, and then work our way back and figure out what theta 1 is. So let's just, what I've done is so this is a light ray coming in, here's going parallel to the surface of the second interface. Now, the angle between the flat surface, horizontal surface, and this other surface is 70 degrees. And because this is a right triangle, theta 4 is going to be 180 minus 70 minus 90, which is going to be 20 degrees. So this angle here is 20 degrees. Now the angle between the normal and the light ray is that critical angle that we just talked about. So when this number is greater than, when theta 3 is greater than some value, then you will get total internal reflection. If it's less than a certain angle, then you'll get some refraction. But we know that theta 3, the sine of theta 3 times N2, so N2 is the material of the wedge, is going to be equal to the sine of this angle, which is 90 degrees, times N1. So we get the sine of theta 3 is N1 over N2, or sine of theta 3 is 1 over 1.5. So that's using our total internal reflection information. Okay, so we're going to take the inverse sine of 1 divided by 1.5. So I get theta 3 is equal to the inverse sine of 1 over 1.5, which is 41.8 degrees. And if you remember back to the lab, that's pretty close to what we measured. So that is angle theta 3. Now we have theta 4, we have theta 3. What we're trying to find is this angle here, because if we draw two vertical parallel lines, theta 5 and theta 2 are going to equal each other. Interior angles, transversal, that kind of stuff. So if we can find theta 5, then we know theta 2, and once we know theta 2, we can find theta 1. So that's the process. So we know that theta 5 is equal to, we have a 90 degree angle here, so it's going to be 90 minus theta 4, which is 20 degrees, minus theta 3, which we just calculated. So that's going to be 90 minus 20, because we had 70, 90, 20, minus this 30, 40 some degrees, 41.8 degrees, 41.8 degrees. So if we do that math, we'll get 90 minus 20 minus 41.8. So we get 28.8 28.2 degrees. So that's theta 5, but that's also equal to theta 2, 28.2 degrees. Okay, so that's the angle that the refracted angle that we have. Theta 1 is going to be bigger because we're going from here, we're going from lower index of refraction to higher index. So that means theta 2 is smaller than theta 1, or theta 1 is larger than theta 2. So to find theta 1, we use Snell's law again. N1 sine of theta 1 equals N2 sine of theta 2. And if you solve for sine of theta 1, you get N2 over N1 sine of theta 2. So N2 is 1.5, N1 is 1. Theta 2 we just calculated to be 28.2 degrees. So the sine of theta 1 is 1.5 divided by 1 times sine of 28.2, which is 0.709. Theta 1 is the inverse sine of 0.709. And I get 45.1 degrees. So that's the answer I'm looking for. Not that particular answer, but for this particular problem, that's the case. But what if we look at it the other direction? We went from down here backwards. What would happen is if I gave you theta 1, what you would do is you'd calculate theta 2. So theta 2 would be, theta 1 was this 45.1 degrees, but the refracted angle is smaller, 28.2 degrees. So that angle here, this ray then would run into this surface at that angle, 28.2 degrees plus 20 degrees, which would end up being this 41.8 degrees. Is that actually what works out here? No, actually what we did is we add this and that. So this is 28.2. This one is 20 degrees. That gives you 48.2. But the angle that we're looking at relative to this second surface is the normal. So you take that 48.2 and subtract that from 90, and you would get 41.8 degrees. And that 41.8 degrees would bend to 90 degrees here and go along the surface. So what you can see is that, if this angle here is, so what's going to make this thing have total internal reflection? Is it a smaller theta 1 or bigger theta 1? Well, if we make this smaller, this is going to be even smaller, which actually is going to make this angle big. It's going to make this angle smaller, which makes this angle bigger, which means it's going to be more likely to internally reflect. So actually, if theta 1 is less than this critical angle we just came up with, 41.5 degrees, then we get internal reflection. These angles are actually the ones that are going to go out. The low angle ones are going to go out, but the straighter ones are the ones that are going to go in and reflect internally. Okay, so you can watch that again if you don't understand. But basically, we use that critical angle for total internal reflection to find theta 3. Knowing theta 3 and theta 4 from the geometry of the wedge, we can calculate theta 5. Theta 5 and theta 1 are equal to each other because of parallel lines, these two parallel lines and this transversal. Once we have theta 2, then we can find theta 1 using Snell's law. And that's how the problem works. So aren't you glad I told you how to do it? Refraction. Now when it comes to lenses and mirrors, what I'm going to ask you to be able to do is the 6 different scenarios that we went over in class. So what I will do is I will tell you which recordings to watch, because I don't need to go through that whole, it's going to take a long time for me to do it. But basically you have 3 scenarios. You have, and these are all with concave mirrors. So you have the case where the object is at twice the focal length, greater than twice the focal length, between the focal length and the center and inside. So you have those 3 scenarios. And then you have the convex lens with the same kind of combination of 3 situations, where it's out twice the focal length, between twice and 1 times the focal length, and inside. So you should be able to draw the lens, the ray diagrams for those 6 scenarios. Also use the lens and mirror equations for those situations. So there's not going to be any convex mirrors or any concave lenses. It's all going to be the scenarios that we talked about. And they look very similar to each other. They actually are the same if you realize that the focal length for the spherical mirror is 1/2 the radius. So be able to use these given 2 out of 3 things, 2 out of these 3 quantities, where P is the object distance, Q is the image distance, and R is, in this case, the radius. Here is the focal length. And also then be able to look at the change in the heights. So the height of the image over the height of the object is equal to negative, let's see which way that works. In this case, you're going to end up with an image that's shorter. So it's going to be Q over P. The negative sign tells you whether it's inverted or upright. So negative means it's inverted. If this whole thing comes out to be negative, it means it's inverted. If you have positive Q and positive P, you get a negative height ratio, which means it's inverted. If you have a positive P and a negative Q times a negative, you'll get a positive number here. And that way, positive means it's upright. And so this tells you how much the image is greater or smaller than the object is. And it applies for both of these equations, whether it's the ray diagram or the lens, lens equations or the mirror equations. Okay, so that's it for chapter 22. Like I said, if you just write this stuff down, you're not going to know what you're doing. You need to go back and look at the 2 handouts that we did for mirrors and for lenses, and then also look at the examples we did in class. Okay, chapter 13. So 2 main things in chapter 13. We have the spring mass situation. So you can think of that as a mass that's on a frictionless surface with a spring like this, or you can think of it as a mass and spring where the acceleration due to gravity is 0. And in both of these cases, the only force acting on the mass is the spring force. So if you compress the spring this way, it's going to want to push to the right. So when it moves to the right, you're pushing to the right initially. but then you'll get back to its equilibrium length, meaning there's no force to the spring, but then it'll have some inertia, so it'll continue on and then stretch the spring and then want to pull it back. And that interaction results in a harmonic x versus time, as well as a harmonic velocity versus time and acceleration versus time. And if you solve the second order differential equation, you find out that there is a relationship between the frequency at which the spring mass system oscillates and the spring constant and the mass. So that's the relationship. The frequency in hertz is equal to 1 over 2 pi. K is in newtons per meter. Mass is in kilograms. They end up having the same units. So we did a problem in class. Basically, you're given 2 out of 3 values. Calculate the third. So I could give you the spring constant and the mass. You could calculate the frequency. I give you the frequency and the mass. You can calculate the spring constant. I give you the frequency and the spring constant. You calculate the mass. And you just have to make sure that the units are correct. Newtons per meter for spring constant, mass kilograms, frequency in hertz. The one last relationship is the time it takes for one complete oscillation is 1 over the frequency. So this is your period in seconds, and this is your frequency in hertz. So I could tell you enough information to calculate the period. You know, it oscillates 10 times in 8 seconds. 10 times in 8 seconds would be 0.8 of a second per oscillation. And then you can find the frequency, and then if you have the frequency in one of these other 2 things, you can calculate the third thing. So there's really 4 variables here. It's period, frequency, spring constant, mass. So given 3 out of the 4, actually 2 out of the 4, you can calculate the other 2 because we've got 2 equations, this one and this one. So we need 2 equations and 2 unknowns. So again, we did an example in class like this, and it won't be exactly the same. It might be different variables, but it's, you know, reasonably simple to solve for the third variable given 2 of the other variables. Okay, the second thing in this chapter was waves on strings, specifically standing waves. So what we did there is we had a string which was anchored at both ends, and the string had a certain length L, and the conditions under which you get a standing wave are such that the velocity of the wave, the speed of the wave, is related to the wavelength of the frequency and the length between the ends of the string. So one of the variables is length, so that's units of meters. Then you've got the wave speed on a string is equal to the square root of f over mu. So this is the tension in the string in newtons. This is the mass per unit length. So that's got units of kilograms per meter. And the units for velocity are meters per second. So that's your wave speed. Now for any waves, you've got the relationship between wave speed, wavelength, and frequency. So if you want a string to vibrate at a certain frequency, you need to have the length sufficient and you need to have the tension set So the wave speed works out. So the third result, the third equation, is that for the fundamental frequency, under those conditions, for the fundamental frequency, the wavelength is equal to 2 times the length between the two ends. And for the second harmonic, which is a higher frequency, the wavelength is shorter, and that's equal to L. And the third harmonic is going to be equal to the wavelength is going to be, what is it going to be? Well, this is a half. Then we take 2/3, so it's going to be, this is be 2L divided by 2. This is 2L divided by 3. The fourth harmonic, lambda, has to equal 2L divided by 4, which is L over 2. So you can see the wavelengths get shorter as you get to higher frequencies. Now, typically, what we do is we calculate the first harmonic, and if we combine these together, we'll end up with that we solve for the frequency, it's V over lambda, but lambda is 2L, so we get 1 over 2L times the square root of F over mu. So the fundamental frequency for strings is a function of the length of the string. The longer the length, the lower the frequency. Think about guitars versus bass guitars. So the longer the string is, the lower the sound is going to be. This is your tension in the string. The lower the tension in the string, the lower the note. And the bigger the string, the mass per unit length. So this kind of puts all of these together in a nice simple equation. And again, I could give you 3 out of 4 of these things, and you could calculate the fourth one. So it may not be exactly in this form. You may have to solve for F or mu or L, but it's just algebra. And then the higher harmonics, instead of using this stuff here, it's easier just to say that the second harmonic is 2 times the first harmonic, and the third harmonic is 3 times the first harmonic, and the fourth harmonic is 4 times the fundamental frequency of the first harmonic. And if we were to plug these into here, we'd end up with these. We'd end up with, if we did it directly, you'd have 2 times this, so it'd become 1 over L times the square root of F over mu, and then this one would become, you'd have, what would you have? You'd have 3 over 2L square root of F over mu, and here you would have 2 over L square root of F over mu. So you could rewrite these in terms of the tension and the mass per unit length, but I think it's easier just to worry about the fundamental frequency using this equation, and then to get the higher harmonics, you just multiply it by, you just keep incrementing this multiplier by 1. This 1 times the fundamental is 1 times the fundamental. The second harmonic is 2 times the fundamental. Okay, so that's chapter 13. Then we have 14. So what do we have? Well, we have the speed of sound is equal to 331 meters per second times the square root of the absolute temperature divided by 273, where T is the temperature in degrees C plus 273. So if I give you the temperature in Kelvin, Celsius, you have to convert it to Kelvin by adding 273. Okay, so you're in the problems for sound, you're either given the speed or you have to calculate the speed from the temperature. Now, what kind of problems could you have? Well, Doppler effect. What the Doppler effect is the difference between the sound that an object produces and the sound that a observer observes because of the difference in the speed of the object and the source. And the equation says the frequency of the observer is equal to the frequency of the source times the speed of sound minus the speed of the source divided by v plus the speed of the observer. And what I said in class was that if two objects are coming towards each other like this, then the frequency of the observer is greater than the frequency of the source. Whereas if they are going apart like this, then the frequency of the observer is lower than the frequency of the source. So you just have to choose the correct signs to make that happen. So one objective towards is you could have one not moving at all and the other one moving towards it like that. That would be towards. You could have the second one moving, and so this is my object. This is my source, sorry. So here's the source, here's the observer. So all three of these scenarios are moving towards each other. And actually you could even have them where I was just thinking about even if you have the case where here they're still moving relative towards each other. So if this one's moving faster than that one, they're still relatively moving towards each other. So that's also another scenario, moving apart. Likewise here, you could have this person stationary, this one moving. You could have this person moving that way and this person stationary. You could also have this person moving faster than that person. So again, they're relative to each other. They're moving away from each other. So these are all cases of moving apart, and these are all cases of moving together. The example I'll give you, the problem I give you will be fairly obvious. So you should be able to reason through the sign conventions of what's going on. But again, the key thing is that they're moving towards each other, then the frequency of the observer is higher than the frequency of the source. So, you can think of like this one here where they're moving towards each other. They're moving towards each other until they cross, and then they're moving away from each other. So you can switch, go from one scenario to another, depending upon whether it's before or after they cross paths. Okay, what else do we have? Just pause for a second here. Okay, we talked about sound intensity level. That was today. So the key thing there was there's two ways of looking at it. You can measure sound level in decibels, and it's defined as 10 times log base 10 of the sound intensity level I divided by 1 times 10 to the minus 12th watts per meter squared. So you should be able to go from one to the other. If I gave you decibels, be able to calculate I. If I give you I, calculate decibels. If I give you I, it's pretty easy because you just plug into this equation. Now to go the other way, you've got to do a little bit of solving logarithmic equations, but we did that a couple times in class. So be able to switch from one to the other. The other two things are that multiple sound sources add I. So you don't add decibels together. So for 50 decibel sound plus another 50 decibel sound does not equal 100 decibel sound. What you have to do is you have to convert 50 decibels to I and then double it. And then what that double the value of I, you have to then back it out to decibels. And we saw that doubling the number of sound sources increased the sound level decibel-wise by about 3 units. So that, of course, is, you can look at 4-12 lecture if you want to learn about this. And then there was the case of distance, how the distance has affected the sound level. And it has to do with the surface area of a sphere. So if you have two distances, distance 1 and distance 2, you take the sound level. Actually, I should do it the other way around. So let's say you're given I1 and you're going to move to a new distance. You take the sound level at distance 1 and you take the ratio of the distances. Now we know if you go further away, then the sound level should go lower. So we know that it has to be R1 over R2, and it's squared because of the fact that the sphere surface area is 4 pi r squared. It's r. So if R2 is greater than R1, this is going to be a number less than 1, and you square it, it's going to be a number less than 1. And so be able to use that. And again, we went through that today. So again, you could be given the decibels at the first location. Then you could calculate the intensity at I at the first location. Then you would use this equation to find the intensity at the second location, either closer or nearer, and depending upon these ratios, and then you could back your way out to find the decibels, which we did this morning. And then the final thing is tubes, and we said we'd only deal with tubes open at both ends. So if you have a tube and you have some way of generating energy, putting sound energy in the neighborhood of this tube, what will happen is you get a standing wave inside the tube. And just like a string, you get the relationship between the wavelength of the fundamental frequency and the length of the tube. And it's that the wavelength is twice the length of the tube, just like for a string, it was twice the length of the string. You have this relationship between wavelength and frequency. Now in this case, the velocity is not a function of the string. It's not a function of the tension in the string or the mass of the string. It's a function of the speed of sound. So if you solve for the frequency, the fundamental frequency for a tube open at both ends up being 1 over 2L, which L is the length of the hollow tube, or the tube open at both ends. And instead of multiplying by the square root of F over mu, you multiply by V. Where V is the speed of sound. And L is the length of the tube. And just like with the string, you can also generate harmonics, which are higher frequency sounds that are multiples of the fundamental frequency. And they don't all come out with the same energy. You can come out with different energy levels for different harmonics for various reasons, which we don't go into in the class. And so the relative ratio of the different harmonics give you the characteristic sound of the instrument. I guess one instrument would be a tube, but that would not be very easy to play. So things like clarinets, flutes, trumpets, trombones all sounded uniquely different because of the different contributions of the different frequencies, the harmonics. So that's the tube. So most likely I'd give you the length of the tube. I might give you the temperature where you calculate the velocity, and then you have to calculate the fundamental frequency. Or I could give you the frequency and ask you how long does the tube need to be. So that is it